Hey guys, in this video we're going to talk about Chapter 8, Section 2, Applications of Geometry. So the first thing we're going to talk about is volumes of revolution. In the last section, what we did was we found the volumes of three-dimensional shapes by adding up an infinite number of cylinders or rectangular slices. So we're going to be pretty much doing the same thing here, except we have to create our own three-dimensional shape based on whether or not they tell us to rotate across the x-axis or the y-axis. So let's just get into this example. It says the region shown is rotated around the x-axis. Using the strip shown, write an integral giving the volume. Then we're going to evaluate the integral. So here we have a two-dimensional region. You can kind of see it's like a green triangle bounded by the curve y equals 2x, as well as the x-axis. And basically, what you should try to see is what would happen if we rotated this thing around the x-axis, right? What kind of shape would it sweep out? And I'm going to do my best to draw this. So if we rotate it, it's going to sweep out a 3D shape, and it's going to look something like this. So it's going to kind of look like a cone. And here is 3. And then when we rotate this thing around the x-axis, this little strip is going to come with it. And the shape that it's going to sweep out is going to be a little cylinder. So let me try to draw this here. Okay, so we have this little cylinder, and then it has a radius of r. Let's call it r. So that's going to be my radius. And then the rest of this region is going to be green. So hopefully you guys can see this. I'm not really, a Bob Ross here, but hopefully you guys can kind of visualize what's going on here when we rotate that two-dimensional shape across the x-axis. It sweeps out this shape. So how do we take the volume here? Well, we can see that what we're given here is that the thickness of this strip is delta x. And so this is telling me that I'm going to integrate across the x-axis, right? So we can see that this is one of those shapes that the radius changes as we move along in our integration. Because if we were to put a little strip here, we can see that the radius of this guy is much smaller than the one that I drew before. So the radius is changing as we move along the x-axis. So again, what we have to do, let's just begin to set up our integral. So we are integrating with respect to x. Again, the key indicator here is that we're given delta x is the thickness of the strip. So where do we start? We're starting at x equals 0. That's where we start adding up our little cylinders. And then we're going all the way up until x equals 3. And what are we integrating? Well, we're integrating the surface area of the cylinder, so pi r squared, times the thickness gives us the volume of the cylinder. So the thickness was dx, or delta x, and our surface area is pi r squared because that cross-section is a circle. But we want to get r in terms of x. And this is not going to be hard to do because, look, this curve right here was y equals 2x. This, maybe I'll do it in purple actually. This guy right here is y equals 2x. All right. And the radius, we can see just, a random spot. Could we write this radius in terms of x? Well, yeah, because it's just the height, right? So this point right here on our purple curve is just the point x, comma 2x. And that's telling us that my height, aka my radius, is 2x, right? So that's what we're going to plug in here for r, is just 2x. So we get pi times 2x squared dx. Now what I can do is I can pull out the 4 pi, right? Because 2 squared is going to give me 4. So I'm going to pull out that 4 pi in the front. And what I'm left with is the integral from 0 to 3 of 4 pi. And then on the inside is going to be x squared dx. And I can integrate this guy. So this is going to be x to the third over 3 from 0 to 3. And I'm going to multiply this by 4 pi. So if I plug in 3 by the in for x, by the fundamental theorem of calculus, I have 3 to the third over 3 minus 0 to the third over 3. And that is just going to give me 9 on the inside. 4 pi times 9 is going to give me a volume of 36 pi. So this is our answer here. This is the volume. This is the volume of this three-dimensional shape that we created by rotating this two-dimensional shape across the x-axis. All right, let's go ahead and do another one. A region can be described as bounded by y equals x squared, y equals 0, x equals 0, and x equals 1. All right, let's go ahead and draw this. Let's do the two-dimensional version first, because we can see that we're going to rotate it about the x-axis to make a 3D shape. But let's draw the 2D shape first. So first thing is I always start with like the lines, like the vertical and horizontal lines. And I have 3 of them. I have y equals 0, so that's going to be this horizontal line. This is y equals 0. Then I have x equals 0, which is just this vertical line that goes, it's basically the y-axis. This is x equals 0. And then I have x equals 1, which I don't know, maybe it's right here. Maybe this is x equals 1. All right. And then it's going to be bounded by y equals x squared. So I can start at the leftmost bound, x equals 0. And for y equals x squared, well, I'm going to have a point right there. And then, maybe if this is the point, maybe if this is x equals 1/2, when I plug in 1/2 into x, I get 1 over 4. So maybe this is the point, 1/2 comma 1 over 4. And then at the very edge of the bound, when we plug in 1 into x squared, we get y is equal to 1 squared, so y equals 1, which corresponds to the ordered pair 1 comma 1. So maybe that's this point right here. This is 1 comma 1. And then we can connect the dots, so it looks something like this. Oh, that was bad. Let me try it again. All right. Cool. Okay. Oh, that was even worse, I think. Let's see. Okay, I think that's as good as we're going to get. So this is my region. This is the region bounded by x squared. Let's actually shade the region that I'm talking about. It's bounded by the 3 lines and the function y equals x squared. So this is the region that I'm going to rotate about the x-axis. I'm actually going to get rid of some of this stuff. I just want to show you guys the picture. So let's see what happens when we do this. So now we're going to imagine rotating this about the x-axis so that it kind of like folds over the x-axis. Okay, so let me try to draw this. I'm gonna just do a rough sketch here. Every sketch of mine is rough. So we have this guy, kind of looks like that. Oh, maybe a little bit more curvy. And then it's gonna be like this. It kind of looks like a horn. Very like skinny cone. Okay, so that's our very rough sketch. And here we have x equals 1. This is what's bounding it by x. Great. Okay, so basically we're trying to find the volume of this region. And what we can do is we can just draw like an arbitrary little strip, just like the previous problem. And here we're rotating across the x-axis. So again, I'm going to have my thickness be delta x. And when we rotate that around, it's going to, again, make a small little cylinder. So there's my tiny little cylinder. That strip. And then it's going to have a radius just like before. And I hope you guys can see the pattern here, what the radius is going to be in terms of x. Well, remember guys, this curve right here that I'm doing, I'll do it in purple again. This guy was x squared, wasn't it? Right? So this little point right here, this little point is going to be x comma x squared. And the height, again, is going to just be x squared. That's the y value. So the height is the radius, and the height is going to be x squared. That's the distance from the x-axis to that purple curve. All right, so again, the radius is going to be equal to x squared. So what's my integral going to look like? Well, again, I'm creating these little cylinders along the x-axis starting at x equals 0. That's a good place to start, right? We're starting at x equals 0 and we're going all the way up till x equals 1. And what am I integrating? Well, I'm trying to figure out what the volume of the shape is. And so the volume of the little cylinders is going to be pi r squared, again, times dx. Dx meaning delta x for the thickness. Well, we just said that r in terms of x was just x squared. So this problem becomes, we're finding the volume of this thing. We're going from 0 to 1. And I'm going to bring out that pi. R was x squared. And we're going to square it. Okay? So now we just have to evaluate this guy. So this is going to be x to the 5th over 5. I'm just integrating x to the 4th. And we're evaluating from 1 to 0. So this is going to give us pi times 1 over 5 minus 0, which is just going to give us pi over 5. So this is our volume of this little horn shape. So I encourage you guys to pause the video here and see if you can do this one. So again, the first thing I notice is that we're rotating across the x-axis. So we're given a region, and what I'm going to do is I'm going to sketch this region as a two-dimensional shape first. So let's go ahead and do that. So I'm going to have this guy right here. I'll start with my lines. I have y equals 0. That's going to be this guy, this horizontal line. I have x equals -1. That's going to maybe be right here. This is x equals -1. I have x equals +1. Okay, so those are my lines. And then I have the function y equals the square root of x plus 1. So let's go ahead and sketch that. I always start sketching at my bounds. So like the first bound is -1. So I put in -1 into this function for x. And I get y equals the square root of -1 plus 1. And that's just going to give me y equals 0. So the ordered pair there is -1, comma 0. And I'm going to plot that right here. So that's 1 point. And then, I can pick another point. I like the point 0. If we plug in 0 into this curve, we get 0 plus 1, or into the function, rather. And I just get that y is equal to square root of 1, which is 1. So we have another point 0, comma 1. So maybe like this. And finally, when we plug in this upper bound, 1, into the function, we get y equals the square root of 1 plus 1, which is just the square root of 2, which is approximately, approximately 1.4. So approximately 1.4. So maybe like that. I don't know. So it's going to kind of look like this. All right. So the region that I'm interested in is this guy. This is the region bounded by the curve and the 3 lines. Cool. All right, now we got to rotate this thing across the x-axis. I'm going to draw a little strip right here. I'm going to draw a little strip. And this thing is going to have a width of delta x. And that's going to turn into our thickness when we rotate it. So let's go ahead and get a little picture going. Get a little picture going. So let's see. Okay, so maybe we have something like this. And then we rotate it. And maybe it looks like this. Okay, so not the prettiest picture, but I hope you guys are able to see this. Let's draw our strip. So again, I hope you guys are seeing the pattern here. What do you guys think the radius is going to be of this little disc? I don't know if you guys met my parents' house, and they live pretty close to a farm. There's a chicken or a rooster going crazy in the background. So here's my little radius right here. This is R. And I hope you guys can see the pattern here. What is this ordered pair? Well, a point on this curve is just x comma square root of x plus 1. Right? And the height, again, is the radius. So the radius here is the square root of x plus 1. All right, so we're going to set up our integral. So where are we starting and where are we ending? Well, remember, this guy was x equals -1, and this other guy this ending bound is x equals 1. So if we start with our disks down here at the very edge, we're starting when x is equal to -1, and then we're just adding more and more disks all the way up till we get to x equals 1. So our lower bound, we're going from -1 to +1, and we're integrating, again, pi r squared times dx. The surface area of the cross section, which is a circle, times the thickness. So our radius we just established was square root of x plus 1. So we have -1 to 1, I'll put the pi in the front, times the square root of x plus 1 squared dx. Well, what's cool about this is that the square cancels out the square root, and we're just left with pi -1 to 1 of x plus 1 dx. All right, so this is pretty easy to integrate. This guy is going to be x squared over 2 plus x. We're evaluating from -1 to 1, and we can't forget about the pi in the front. So let's evaluate this guy. So we get pi times 1/2 plus 1 for the upper bound minus -1 squared over 2 plus a -1. Okay, let's go ahead and simplify this thing. So we get 3/2 minus, well, this is just going to be 1/2 minus 1, which is just -1/2. And of course, those double negatives make a positive. So we have 3/2 plus 1/2 is 4/2, which is 2. Okay, so our volume here is going to be 2 pi. Let's do another example. So again, I'm doing a bunch of them where we're rotating across the x-axis just to give you guys some intuition and to see what's going on here. I know these things can be tricky to visualize. I have a hard time visualizing some of this stuff myself. But, it gets easier once you do more and more of these problems. And, as the pattern here is the radius. If your function falls in such a way that that the radius is the height, that's really nice. So let's see if we have that instance again here. All right, so again, I like to start off with my lines first and then my function. So let's do a rough 2D sketch first. We have y equals 0. It's going to be this guy. X equals 0. It's this guy. And then x equals 4. I don't know, maybe it's right here. Okay, so there's my lines. And then we know that the function isn't going past this line. It's going to be basically like trapped in this area, right? Because it's bounded in that area. So I'm going to start. So here's my function, 5x squared. If I plug in 0 for x, I get y equals 5 times 0 squared, which is just 0. So I know the point 0, 0 is on my curve. Then if I get another point that's in between 0 and 4, I don't know, how about, what about 1? If I plug in 1 into the function for x, I just get y equals 5. So I have an ordered pair 1, 5. And maybe it's right here. I don't know. Just getting a rough sketch here. Actually, let's make it a little lower just so we can get a good picture. And then finally, when x is equal to 4, our upper bound, we get y equals 5 times 4 squared. So this is going to be off the picture, but it's all right. We're just doing a rough sketch here to get the idea. So this is 80. So we have 4, 80. Again, rough sketch. So here's our function. And so the region that we're concerned with is the region that is trapped between all of these lines and the function. So that's this guy. And you know the story. We can rotate this thing across the x-axis to get a little horn. And again, same story. If we have a little strip right here and we're calling the width delta x, if we're calling the width delta x, then when we rotate that strip around, we're going to get a disk. So let's see, maybe it'll look something like that. And again, the radius is going to correspond exactly to the height on this curve. So this is going to be the point x comma 5x squared. So we know that the radius is going to equal 5x squared. All right. So let's turn my page. So let's go ahead and set up our integral. Where are our bounds? Where are we going? Well, again, we are integrating with respect to x. So we're starting here, okay, and that is going to be x equals 0. We're going all the way up till x equals 4, right? Because that's what we were initially told, that was our upper bound. And we're going to integrate pi r squared. So again, r is 5x squared dx. Same story here. We're going to pull out the pi, and I'm also going to pull out a 25 because of this. When I do 5 squared, that gives us 25. All right, so let's integrate this guy. So this is going to give us 25 pi on the outside. Then I have x to the 5th over 5 on the inside from 0 to 4. And what I end up getting here is, I end up getting, let's see what we got here. 4 to the 5th divided by 5. Well, that's not really divisible by 5, but 1024 times 25 divided by 5. Yeah, so this is going to give us 5,120 pi, and that is going to be our volume. Okay, let's do another one. So we have a region bounded by the curve y equals e to the negative x, and the x-axis between x equals 0, x equals 1, and it's revolved around the x-axis. Find the volume of the solid of revolution. So again, I encourage you to pause this video and see if you can set up your picture and your integral. Let's do it. So I'm going to start with my lines here and the x-axis. So x-axis, x equals 0, and x equals 1. Okay. And then my curve is y equals e to the negative x. Okay. So if I plug in 0 for x, I get y equals e to the 0, which is 1. So I have an ordered pair 0, comma 1. Right? And then if I plug in you know, if I plug in 1 into this thing, I get y equals e to the negative 1, which is just y equals 1 over e, which I don't know, maybe is like right here or something. So here is my region. Here is my region. And again, same story, we're rotating it across the x-axis. Same story here. So this is delta x. Let's go ahead and rotate this thing. Let's rotate this thing. So maybe it looks something like that. It's probably going to be closer to the x-axis, to be honest. Let's see. We can draw this a little bit better. Okay. Here's my region. And same story. So when we rotate that strip around, we get this little bitty cylinder. And we can see that the radius again is the height or the y value of that function. So this little point right here is going to be x comma e to the negative x, right? So when I set up my integral, I'm again integrating with respect to x. This is the key indicator that I'm going to be doing that, and the fact that it says that we're rotating across the x-axis. That's a good indicator there too. So where am I going, and like from x equals what to x equals what? Well, again, I'm starting from x equals 0. This is my first bound, and I'm going all the way to x equals 1. And I'm going to do pi r. Again, r is going to be the height of that function, which is just the y value. So this is pi r squared dx. And I can rewrite this as 0 to 1. Pi comes on the front of e to the negative 2x dx. So how do I integrate this? Well, all I have to do really is just a simple u substitution. So what I can do is I can let u equal negative 2x. Therefore, du is equal to negative 2 dx. And therefore, negative 1/2 du equals dx. So let's go ahead and plug in that stuff. So we have pi from 0 to 1, e to the u, and du is, dx is the same thing as negative 1/2 du. I can pull out the negative 1/2 in the front. So this gives me negative pi over 2 in the front from 0 to 1, e to the u du. We know the antiderivative of e to the u is just e to the u. So this guy is going to give us, we already said u was negative 2x. So we just have e to the negative 2x. We're evaluating from 0 to 1. And I'm going to give a decimal here just because it's not the best looking, we can't write this exactly. So this is going to give us e to the negative 2 minus, if we plug in 0 for x, we get minus e to the 0, which is 1. And if I put this in the calculator to get a decimal for it, I get approximately 1.36. And that is my volume of this shape right here. A region can be described as follows, bounded by the line y equals 3x, x equals 0, and y equals 6. We want to rotate this region around the y-axis this time to find the volume. So let's go ahead and just give this thing a quick sketch. So again, I like to do my my lines first. So I have x equals 0, so that's going to be this vertical axis right here. Y equals 6, let's just say that's up here. This is y equals 6. And then I have the line y equals 3x. So let's see. At x equals 0, y is also equal to 0. So it looks something like this. And then when x equals 2, y equals 6. So it's going to look something like this. And that's going to be our region. And this time, we want to imagine that this thing is being folded across the y-axis instead of the x-axis. So when we rotate it across the y-axis, it's going to look something like this. And maybe this line isn't as straight as I want it, but all right, so we have this cone, and the idea here is that since we're rotating around the y-axis now, we want to integrate with respect to y. So our strips initially are going to look something like this, where the thickness, instead of dx this time, or instead of delta x, is going to be delta y. It's the thickness of these little strips. And so when we, when we rotate the strip around, it's going to look something like this. All right, so there's our disc. And it's going to have a radius. So here's our radius. And now notice what the difference is here, right? So again, let me make this clear. We're going to do this in purple. This is the line y equals 3x in purple. And so here it is right here. This is y equals 3x. But this time, we can see that the radius is going to be the x width, right? This is the x-axis, and we can see that this thing is going to be, in terms of x, basically. So we want to make sure that our radius is in terms of y, since we're integrating with respect to y. So again, let's try to imagine this. So here's our dy. It's going to be our thickness of the discs. And we're going to start at the bottom right here. And we have a disc here. And then we just keep adding discs all the way until we get to our upper bound. So this is going to start at it's going to start at y equals 0, right? And it's going to go up to y equals 6, as we can see here. That's our upper bound. Pi r squared dy, right? And again, we are integrating with respect to y, so we want to make sure r is in terms of y, right? So we just have to rearrange this guy so that, our radius, which is going to be our x value, is in terms of y. So all we have to do basically is divide both sides by 3 to give us y over 3 is equal to x. So this is our radius. And I hope you guys can see why this is the radius, this x value. So that's what we need to plug in for r, y over 3. We want our radius in terms of y, since we're integrating with respect to y. Okay, so that's our integral. And what I can do is y over 3 squared is y squared over 9. So I can pull out a pi over 9. And when I do that, I'm just left with the integral from 0 to 6 of, oops, didn't mean to do that, of y squared dy. So let's go ahead and integrate this thing. So this is going to give me pi over 9 on the outside. On the inside, I have y to the 3 over 3, and I'm going from 0 to 6. And this is going to give me pi over 9, 6 to the 3 over 3, minus 0 basically. And this is going to give me, let's see. So this is going to give me 72 on the inside. So I get 72 pi over 9, which reduces to 8 pi. All right, so that's our answer. That's the volume of this three-dimensional cone. All right, let's do another example. So here we want to figure out the region bounded by y equals ln x, y equals 1, and x equals 0, rotating it around the y-axis. So let's go ahead and sketch the 2D version first. So we have y equals 1, maybe it's down here. And then perhaps y equals 2 is up here. And then we have x equals 0, so that's going to be the y-axis basically. So our region is going to be in this area. Now we want to graph y equals ln of x. So let's go ahead and do that. If we were to, so basically what we want to do is we want to take the function that we're given, y equals ln of x, and put in y equals 1 and see what we get for the corresponding x value. So that's our lower bound, right? Now when I solve for this, remember ln of x, so log, got ahead of myself. ln of x is the same thing as log base e of x, right? Those are the same exact things. So here what I have is 1 equals log base e of x. And so this is just saying, e to the first is equal to x, right, by these log properties. And so we get x equals e. Okay, so we have the point e comma 1. All right, so that's going to be, I don't know, maybe right here or so. Okay, then we have, if we look at our upper bound here, again, y equals ln of x is the curve. We're putting in 2 for y, so 2 equals ln of x. Doing the same thing, we have 2 equals log base e of x, and so e to the 2 equals x, so it's going to be e squared. All right, so I don't know, maybe it's like right here, something like that. All right, so here is our region. There's our region. And I can draw a strip if I want to. with a thickness of delta y. So there's my strip. And this time, again, I'm rotating across the y-axis. So let's go ahead and do that. Okay, so maybe it looks something like this. And then we have this disc. All right, so my starting point here, where does this region start in terms of y? Well, it starts right here at y equals 1. So we're going from y equals 1, and the upper bound for the y is y equals 2. So that's our ending integral. dy, that's the thickness of the disk, and we want to multiply by pi r squared. But we want r in terms of y. So again, just like the previous problem, this r is going to be how far out this disk extends to the right. This is going to be our radius. And so that's going to basically be our function, right? So we have y equals ln of x. And to get x by itself so that we can plug that into for our radius, we have to raise both sides to, or we have to take e and raise both sides with e as the base. So, okay, so we have e to the y equals e to the ln of x, right? Since e and ln are inverses, those cancel out and we're just left with x equals e to the y, right? So that's our x value in terms of y, which is our radius. So I'm going to plug in e to the y in for r. That's our radius. Okay. So let me erase some of this stuff down here. And we can pull out that pi. So if we pull out the pi, we're just left with 1 to 2 e to the 2y dy. Okay. From here, I can do u substitution just like before with the e problem. So we have let u equal 2y, and therefore du is equal to 2 dy. Dividing both sides by 2, I get that dy is equal to a half du. So making those substitutions, let's do that. Okay, so from here I can pull out the 1/2 in the front. So I'm just left with pi over 2 in the front from 1 to 2, e to the u du. And of course, the antiderivative of e to the u is just e to the u. So we're left with e to the u, and u is 2y. So we have e to the 2y, and we're evaluating from 1 to 2. And so we get pi over 2 e to the 4 minus e to the 2. Again, plugging in 2 for y minus plugging in 1 for y by the fundamental theorem of calculus. And I'm not going to bother simplifying this anymore, so that is going to be the volume there. All right, let's talk about another application to definite integrals. We can also use definite integrals to find the arc length. And And I'm going to show you, basically, I'm going to give you the formula, and I'm going to try to give you an idea of where the formula is coming from. So arc length is literally like, you know, if you have a curvy shape and you want to measure it, you can't use a ruler, right? Because it's going to give you an approximation. It's not going to give you an exact answer. But we can use calculus to find an exact answer. I'm going to show you how. So let's consider this piece right here, in dark blue. What if we wanted to find the length of that? How would we do it? Well, what I'm going to show you is basically I'm going to take a tiny little piece. I want you guys to imagine that this is like so small that there's no way you could see it. Okay? This little green piece right here, and I'm going to blow it up over here. So I'm going to blow it up so that you guys can see this, but I want you to imagine it's so tiny, okay? The idea here is that I'm going to add up, basically I'm going to make this portion so small right here that it looks like a straight line, right? And then I'm going to add up all the straight lines to figure out what the length of that arc is. That's the idea here. All right, so I'm going to blow up this tiny little piece over here, and it's going to look something like this. And what I'm going to do, it's so tiny, right? And so what I'm going to do is I'm going to call the x component, because it's so small, it's going to be dx, right? This tiny little width. And then I'm going to call the height, the y component, dy, right? And then I'm going to connect these guys together to make a hypotenuse, and I'm going to call that hypotenuse ds. And you have to imagine that this is so small, infinitely small, right? And now what's cool about this is I can use Pythagorean theorem, right? To get the length. That's what I'm trying to do. I'm trying to find the length of this straight line. And remember, it's straight because we're zooming in so close to where it looks straight, okay? That's the intuition here. All right, so here's Pythagorean theorem. We have dx squared plus dy squared equals ds squared, all right? Now, again, I'm trying to find ds. That's the goal. This is ds, this length, and I have infinitely many of these that I'm going to add up, right? That's the idea there. So I'm going to take the square root of both sides to get ds isolated. I'm just showing you guys where this formula is coming from, so you're like, what the heck is that? Like, where did this come from? Hopefully this will give you some intuition. Okay, so I'm going to do a magic trick. All right, and that's what we do a lot of times in math. We just we use mathematical rules to force things to look how they want, right? So what I'm going to do, this little trick that I'm going to do, is I'm going to factor out a dx squared on the inside of the radical. When I do that, when I factor that out, this is just going to be 1 plus dy over dx squared, okay? Right? If I distribute this dx squared back in there, I'm back where I started at dy squared, okay? So that's a little trick. This guy, dx squared, if I take the square root of him, it's just a dx on the outside, right? I'm left with 1 plus dy over dx squared, dx on the outside equals ds. Okay. What's dy dx? Well, that's the derivative, right? If this function that we're looking at is f of x, then the derivative is f prime of x. And so we get that ds is equal to the square root of 1 plus f prime of x squared, right? So this is ds. This is just a tiny little, oops, let me do this in green. This is a tiny little piece. This is ds, right? And so this is where the integral comes in, right? This is part of my formula. This is most of my formula, this part. The integral comes in. We're starting at an x value of a, and we're going all the way to b, and we're adding all of these little ds's up to get the arc length. Pretty freaking cool if you ask me. All right, so that's where that formula is coming from. Now what we're going to do is actually apply the formula. And in your homework, I am actually going to encourage you to use an online integration calculator because we've already talked about integration techniques. That's not what I want you to get out of this lesson. I want you to, first of all, see where the formula came from. And hopefully you guys did kind of get an intuition of where that formula came from. And I want you to use it. Okay, so I'm not going to focus too heavily on using integration tables and just finding these ugly antiderivatives. This one, we can use, I'm going to show you guys how to do it by hand, but yeah, so let's go ahead and do this one. We're trying to find the arc length from 0 to 1. So if you want to, you can go on Desmos and see what this looks like. And we're just trying to find the length of the curve from x equals 0 to x equals 1. So our integration formula, we're going from 0 to 1, right? A to b. And then we're taking the square root of 1 plus f prime of x squared dx, right? Well, we need to first find out what f prime of x is. And I know you guys probably haven't taken a derivative like this in a while, but let's try to recall how we do this. Here's our f of x. Now, we have to use the chain rule here. So we have to multiply this guy on the outside. So we have a third times 3 over 2, x squared plus 2. Subtract 1 from 3 over 2, right? 3 over 2 minus 2 over 2 is 1 over 2. And then we're going to multiply by the derivative of the inside function, which is this guy. So the derivative of x squared plus 2 using the power rule is just 2x. All right, let's clean this up a little bit. So again, this is f prime of x, just the derivative of our function. And these guys cancel, and we're just left with 1/2 square root of x squared plus 2, right? Because this is to the 1/2, times 2x. I'll put that in front. And you guys can see here that these 2's are going to cross divide each other. And we're just left with f prime of x is equal to, let's write it down, f prime of x is equal to x square root of x squared plus 2. Okay? So that's what we needed for our formula, so let's put it in. So we're going from 0 to 1, square root of 1 plus x square root of x squared plus 2 squared dx. And we can simplify this a bit. Remember, the square is going to cancel that radical out. And what I'm left with is 1 plus, well, x squared is x squared. Square root of x squared plus 2 squared is simply x squared plus 2. That radical cancels out there. And then I can clean this up a little bit. Distribute that x squared on the inside to give me 1 plus x to the 4th plus 2x squared dx. Now from here, what you should recognize is that I can write this as x to the 4th plus 2x squared plus 1. And I can actually factor this guy, right? I can factor this trinomial. I can factor this into x squared plus 1 times x squared plus 1. All right, that's just factoring that trinomial. And that's the same thing as x squared plus 1 squared. Well, again, the radical and the square are going to cancel each other out. So what I'm left with is from 0 to 1 of simply x squared plus 1 dx. And this is easy to integrate. This is just x to the 3 over 3 plus x. And we're going from 0 to 1. So all I get here, I get a third plus 1 is going to give me 4/3. And that is the arc length of that curve from x equals 0 to x equals 1. All right, so we want to set up and evaluate an integral to compute the length of the curve y equals x to the third from x equals 0 to x equals 5. So how are we going to deal with this? Well, again, we have to use our formula. We're going from 0 to 5, square root of 1 plus f prime of x squared dx. And our curve is x to the third, so that means that f prime of x, if we take the derivative of that, is just 3x squared. So let's rewrite this. We have 0 to 1, 1 plus 3x squared dx. All right. So from here, I want to say that what you could do is you could possibly use the integration table. Let's see. Let's see, which one will fit this? I believe in the integration table, this one will fit. But it's just too much work for the point, like it's basically, I don't want you guys to spend a whole ton of time like evaluating these crazy integrals in this section because we've already done that. So I'm going to tell you to use your resources, use technology, aka Google. Unless you really want to challenge and you want to try this. But it's not really, we're past that. So Symbol Lab has an integration calculator. I'm sure a lot of you guys already know that, but basically you can use that to find this integral. And I encourage you to use this on your homework as well with these arc length problems, because it turns out that these arc length integrals, they don't have easy antiderivatives most of the time. I mean, this one did. We got away with doing this one, but a lot of them don't have great antiderivatives. So I do encourage you for your homework with these arc length problems to use Symbol Lab. It'll give you the answer. And what I get from Symbol Lab when I do this is 125.68. Okay.